Hello. Today we have a more chill video than definitely the last math video that I created, which was sort of a big production that was almost an hour long and involved animations and whatnot. This is just a chill thing that I decided might be fun to record and upload. It is a presentation that I gave not on August 16th, that is today. It is a presentation that I gave last semester about generating functions. The theme was that we would present to the undergrads something related to the research we are ostensibly doing. So this was mine. I hope you enjoy. Just a quick note, in order to understand this, you're basically going to want to already know what polynomials are. That's the business with like 1 plus 3x squared plus 8x to the power of 17. That's a polynomial. If you don't know about polynomials yet, you will find this very hard to follow, for which I will not really apologize because you're not the intended audience, but you know, come back when you learn about polynomials. I promise this is cool. So, the first thing we want to do is just define a generating function. So here's the sort of formal definition. The generating function for a sequence which has an oath term, a first term, a second term, a third term, and so on, is this series, where, well, yeah, it's easier to start here. The second term is the coefficient, that is the number in front of the second power of x. The third term is the coefficient of the third power of x. The first term is the coefficient of the first power of x, that's x to the 1 is equal to x. And the oath term is the coefficient of the oath power of x. So there is no x there, that's x to the power of 0. And it would continue on. So the ninth term of the series would be the coefficient of the ninth power of x. That is the number in front of x to the power of 9. Essentially, what this does is it stores all the information from a sequence into a single mathematical object. That is this infinite series. For example, the Fibonacci sequence is defined as a sequence where the oath term is 0, the first term is 1, and every subsequent term is the sum of the previous two. So 1 is 1 plus 0, you can take 1 plus 1 to get 2, 1 plus 2 to get 3, 2 plus 3 to get 5, 3 plus 5 to get 8, and so on. A lot of you have seen this before. All of these terms can be consolidated into what we call a generating function. So in this case, with the Fibonacci numbers, we have f of x is x plus x squared plus 2x cubed plus 3x fourth, and so on, where you see the coefficient of the oath term is 0, so there is no constant term, and then these coefficients are 1, representing these ones, then we have 2, 3, 5, 8, 13, continuing onward. Note, we don't really think of this as a function in the usual sense, where you would plug in, I don't know, 3, and try and get an answer out of it. Well, partially because, I mean, at least in this case, 3 is much too large. But even like, I think 2/3 is going to be too large a number for this sequence to actually converge. So yeah, we don't tend to think about this, we as in mathematicians. This is just a guy. This is a guy in his own right. It is a formal Taylor series, an infinite polynomial, if you know either of those terms. Now, there are a couple ways in which generating functions can make calculations simpler. In this talk, I covered 3 of them. The fastest one to explain is probably shifting, which is that multiplying by x has the effect of shifting the terms in the sequence. So, for example, if we start with our initial Fibonacci generating function, you've got the 1, 1, 2, 3, 5, and so on. Multiplying this function by x gives us this new function, where this x becomes an x squared, this x squared becomes an x cubed, the 2x cubed becomes a 2x to the 4th, the 3x to the 4th becomes a 3x to the 5th, and so on. And what you can see here is that if you compare the parts with the same exponents, so this has an exponent of 4, this has an exponent of 4, the term has shifted. Before, the 2 was in front of the third exponent, so it was the third term in the sequence, and now the 2 is in front of the fourth exponent, so it's the fourth term in the sequence. Similarly, multiplying by x squared will shift things twice. While before, the sixth term was 8. Now the sixth term is just 3. So for the sequence corresponding to this generating function, it starts with an oth term of 0, a first term of 0, a second term of 0, and then gets into the 1, 1, 2, 3, 5, and so on. Why is this cool? Well, it's useful if adding shifted versions of the sequence to each other does something special. So for example, if we take x times f of x, that's this row right here, and x squared times f of x, that's this row right here, and add them together, what do we get? Well, just adding term by term, we get the 1x squared, an x cubed from each for a 2x cubed, a 2 and a 1 make a 3, a 3 and a 2 make a 5, a 5 and a 3 make an 8 and a 5 make a 13, and hang on, this sequence is familiar. This looks just like our initial function, x squared plus 2x cubed plus 3x to the 4th plus 5x to the 5th, except it's missing its x term. The initial x term right here is absent. So this is just f of x minus x. And the neat thing about this is, now that we have this expression, we can actually solve this equation, xf of x plus x squared f of x equals f of x minus x. We can just solve that for f of x. It's actually just a linear equation in f of x, even though it looks a bit daunting. So without too much trouble, you can find that f of x is x divided by 1 minus x squared. And I think that's neat. To introduce our next trick, I would like to ask the question, what happens when you multiply two polynomials, or series, with each other? So in this example, we've got an a0 plus an a1x plus a2x squared, and a b0 plus a b1x plus a b2x squared. It's two quadratic polynomials. And if you multiply them together, you see that the first few terms are a0 b0 for the constant term, and, well, it's this. The thing to notice here is that the coefficient of n is the sum of all ai bj, where I plus j is equal to n. What does that mean? That was a bunch of jargon speak. Well, it just means, okay, let's take n equal to 2, for example. If we look at the second power of x, look at the second coefficient, we see that it is a0b2 plus a1b1 plus a2b0. That is, we're taking all the numbers whose subscripts add to 2. 0 plus 2 is 2, 1 plus 1 is 2, 2 plus 0 is 2, multiplying the corresponding entries and adding them together. This mildly weird operation is called convolution, and it actually happens surprisingly often in math. It happens all the time. One common place in which convolution shows up is in adding random outputs. For example, let's say you rolled a 6-sided die and a 4-sided die and added the results. How likely are you to get a 4? Well, let's go through all the options. You could roll a 1 on the d6 with probability 1 in 6, and a 3 on the d4 with probability 1 in 4, or you could roll a 2 on the d6 with probability 1 in 6, and a 2 on the d4 with probability 1 in 4, or you could roll a 3 on the d6 with probability 1 in 6, and a 1 on the d4 with probability 1 in 4 again. All in all, what you're going to get is 1/6 times 1/4 that this first thing happens, plus 1/6 times 1/4 that this second thing happens, plus 1/6 times 1/4 that this third thing happens. And that's going to give you 1/8 in total, and that is your chance of getting a 4. And you can see we've got the same kind of structure here as we did in this convolution. We're multiplying two things from different sides together, and then adding up all the results. So why is this actually useful? What does this have to do with polynomials and convolutions? Well, it's helpful when you're talking about generating functions for probability distributions. So say we have some way of randomly generating natural numbers, where the natural number n appears with likelihood p of n. So that's the chances that you get the natural number n. We say that the generating function for this probability distribution is, well, this sum. So we've got in the coefficient for the second term is the probability that you get 2. In the coefficient for the third term is the probability you get 3. In the coefficient for the first term, that's x, the probability of 1. And in the coefficient of the oath term is the probability of 0. This is slightly different from the generating functions we've seen so far. Instead of the coefficient of x to the n tracking the nth term in a sequence, we track the probability that the output is n. Now the cool thing is, you can find the distribution for adding two results by multiplying the corresponding generating functions. So, for example, a coin flip has even odds of landing heads or tails, so the generating function for the number of heads is 1/2 plus 1/2 x. That is to say, there is a 1 in 2 chance that you get 0 heads, that's x to the 0, and a 1 in 2 chance that you get 1 head, that's x to the 1, or, x. Then we can find the result of flipping a dozen coins by taking 1/2 plus 1/2 x and raising that polynomial to the power of 12. So if you wanted to know, what are the chances that I get 4 heads when flipping a dozen coins? The answer is just whatever the coefficient of x to the power of 4 is in this 12th degree polynomial, if you can be bothered to write that all out. Now, I'd like to pose an interesting question. So the generating function for a regular 6-sided die is this. There's an equal chance of each number from 1 to 6. There's a 1 in 6 chance of x to the 1. That is a result of 1. 1 in 6 chance of getting a 5. So the coefficient of x to the 5th is 1 in 6. And so on. This means that the generating function for rolling 2d6 is this value squared, right? Because 2d6 is just rolling 1d6, adding the result of 1d6. That is what this notation means. Oh, I can highlight things. That's fun. And so multiplying this generating function by itself just gives you the square. And of course, we can, if we wish, actually expand this out. So here is the 12th degree polynomial that corresponds to the generating function for rolling 2d6. So, for example, you have a 1 in 12 chance of getting a 4, and a 5 in 36 chance of getting an 8. The question I want to ask is, are there any other ways to get this distribution rolling 6-sided dice? In order to find the answer to this question, we're going to need our third generating function trick, factoring. Polynomials can be factored. For example, let's factor this polynomial. We notice very quickly that everything has a 1/6 in front of it, so we can take out a factor of 1/6, leaving only the powers of x. What's more, all of these powers of x are at least 1, so we can pull out an x to bring the smallest power down to 0 here. And from here, there are actually 2 ways we can go. And I'm going to be sort of narrating the stuff that's going on the left. You can follow along on the right if you wish. So we have this starting polynomial. We group the terms into the first bit and the second bit. We notice that the second bit, everything is a power of at least 3, so we can pull out an x cubed. And then we notice that we have a repetition of this, a 1 plus x squared in both sides. So we can pull out, there's 1 plus x squared, there's x cubed, 1 plus x squareds, and so we get this factorization. And on the other side, we get this different factorization. Both of these are just the generating polynomial for rolling a 6-sided die. Then, if we want, we can write this, the generating polynomial for 2d6, as the one factorization that we got over here times the other factorization, that we got over here, right? Because both of these are just equal to this term. Now, the magic happens. We have the generating function for rolling 2d6 is this. And if you multiply these out, this will give you the generating function for a 6-sided die, and this will also give you the generating function for a 6-sided die. Here's the trick. We switch the two-term factors with each other. That is to say, the generating function for rolling 2d6 is also this right here. The 1 plus x cubed becomes a 1 plus x, and to balance that out, the 1 plus x becomes a 1 plus x cubed. This will obviously multiply to the same thing that this entire expression does. Then, pulling each half of this back to its own distribution, we get that this half is 1/6 times x plus 2x squared plus 2x cubed plus x to the 4th, and that this guy is 1/6 times x plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th plus x to the 8th. And so, here is the punchline I promised. If we roll a 6-sided die with labels 1, 2, 2, 3, 3, 4, and also a 6-sided die with labels 1, 3, 4, 5, 6, 8, and we add the results, we get the exact same probability distribution as 2d6, as just rolling 2 regular 6-sided dice. In fact, if you do a little more stuff with unique factorization of polynomials, you can prove that this is the only other way you can roll 2 6-sided dice and get 2d6, as long as you assume that the minimum value is at least 1. So, in summary, generating functions are cool. They let you shift, add, and convolve sequences with ease, which is useful if your initial sequence has some recurrence, like Fibonacci, or if it represents a probability, like the 1d6 sequence that we saw. Is this what I use generating functions for in my research? Not really. I prefer generating functions that count things, rather than list probabilities or whatever Fibonacci is doing. You have no idea how uncomfortable it made me to be working with generating functions that have fractions in the coefficients. All this time, I don't like that. I don't like fractions. For an example of something that I would be doing, let's ask the question, how many ways are there to write a given positive integer as a sum of distinct positive integers? So here's a few examples. You can get 3 as 2 plus 1, 4 as 3 plus 1, 5 in 2 ways, 4 plus 1 and 3 plus 2, and 6 in these 3 ways. And of course, you can keep going with 7, 8, 9, and so on. If we let the coefficient of x to the n track the number of ways to write n as a sum of distinct positive integers, then the generating function is this guy. You can see there's 2 for x cubed, 2 for x to the 4th, 1, 2, 3 for x to the 5th, 1, 2, 3, 4 for x to the 6th, which is actually just this infinite product of binomials, which I think is neat. And that's the sort of stuff, well, a very, very simple version of the sort of stuff that I am planning to do for my research. So this was the end of the initial presentation that I actually gave. But as a bonus for my YouTube audience only, here's another slide with the 4th and final generating function trick. These 4 are legitimately basically the only things that you can do with generating functions, but together they make for a really powerful theory. So, okay, remember at the very beginning of this presentation when I said that we don't really think of these functions as actual functions with inputs and outputs? We just think of them as like formal things to do with x? Well, sometimes it can be useful to strategically forget this fact. For example, our generating function for the Fibonacci series was this, 1, 1, 2, 3, 5, and so on, which we found using the shifting trick is equal to x divided by 1 minus x squared. Now, something cool happens when we input x equals 0.01 into this function. So what we get is this expression. I'm not going to read that out. But what that actually becomes is 0.01 plus 0.0001 plus 0.5 zeros and then 2 plus 0.7 zeros and then 3 plus 0.9 zeros and then 5, and so on. Notice that these numbers here are going to be the Fibonacci numbers that we started with. And in the end, what we get is this decimal expansion. 0.01, 01, 02, 03, 05, 08, 13, 21, 34, 55, and so on. It's going to be the sum of all the Fibonacci numbers along hundredth places, basically. Now, this is kind of cool on its own. Like, okay, cool, we have a number that is written out in Fibonacci numbers, but like, so what? Obviously you can do that. You can just write the Fibonacci numbers as the digits of a real number. But the cool part is that we still have this half of the equation. So if we plug x equals 0.01 to the other side of the equality, we get this expression here, which simplifies to 10,000 divided by 9,899. In other words, the Fibonacci number that we just found, that's not a Fibonacci number, but a number with Fibonacci digits, this guy right here, is actually a rational number, a fraction, and its digits are the digits of 1 divided by 9899. So if you just take 1 divided by 9899, you will get a bunch of zeros at the beginning, and then 01, 01, 02, 03, 05, and so on. So if you ever find something online which is like, wow, look at this, if you plug in 1 divided by this wacky number, you get all the natural numbers in order, or all of just the powers of 2 in order. That happens because of a generating function. Every single time, if you look under the hood, there's going to be a generating function there. And I think that's neat. All right. That is actually, for real, the end of the presentation. Thank you all for being here. I say in an empty room, don't worry, I know how the internet works. Somebody will watch this eventually, right? Definitely? Yeah, probably. Okay. Have a good day. All of these terms in this infinite sequence can be consolidated into a generating function. I just realized that you're going to be able to tell when I cut because I'm moving my mouse around, but that's the price that we have to pay in making a video, making a sort of low effort video for fun, which is what we're doing. Okay. Moving on. Well, yeah, we are moving on, but what are we saying? It's been so long since I've given this presentation. This is kind of a weird looking operation, but, oh, that spacing. I hate that spacing. Okay, we're going to have to live with that. The spacing again. And you can read off the other values here. I don't know why this is highlighting for me. What do you want me to do? That's a phone number? I see. I should do like an outtakes for this video. I don't know if that's more effort than I want to be putting in. I'll probably do it.